like to talk about melody harmonization. This is joint work with Pedro Magalesh and Bas de Haas. And this is actually something that was created out of my undergraduate project studying artificial intelligence. So it's automatic melody harmonization, which in itself is nothing new, or it has been done before a lot of times. But what I want to show you is a simple and modular approach that is functional, of course. Under the hood it uses a harm trace, which is a functional model, and Haskell for creating MIDI files, reading and writing the MIDI files. I'll explain something about harmony very briefly, and then I'll explain the workings of the system and some experiments we carried out. Speak up. Can you hear me now? Okay. So what harmony really is the sounding of simultaneous notes, simultaneous sounds. And those are, when they are arranged in certain configurations, we call them chords. And what we're going to focus on, what we focused on in the harm trace is, in the F-harm, sorry, is triadic chords. Those are chords that are created out of 3 notes. I'll give you some examples here. If you create a triadic chords on the G note, you take the G note, skip the A, take the B, skip the C, and take the D, and this pattern you can create on every note. One special feature about these kind of chords is that every melody note appears in exactly 3 chords. So, for example, if I take the note G, it appears in the chord G as the lowest note, in the chord E as the middle note, and in the chord C as the highest note. Just to see, I'm using this blackboard font as a notation for chords and the normal notation for just notes. So with this special feature of these triadic chords, we can use it to harmonize things, and we can use it to create interesting patterns for a melody. So one way to use this is in harmonization of a melody, and I will give you an example of a simple melody, which in itself is of course boring, like this, and I'll be the one that using MIDI keyboard instead of dubstep. So this is boring, of course, but if we add chords, we can enrich the music and create nice, interesting patterns, like this one. Well, of course, a melody has a multitude of harmonizations. Because you can choose many chords with different melody parts. Which chords to pick and which sequence of chords you pick, this is all constrained by the rules of a harmony theory. So what it really boils down to in harmonizing a melody is the selecting of the best matching chord for a melody segment and the best overall sequence of chords. So the way we implemented this is in F-harm. And I told you this is a modular system which is made out of 4 independent parts. The first step is a generating step in which chords are generated for each melody note. The triadic chords that I just showed you. In the second step, we select sequences of chords out of all the possible chords for a melody note. Those sequences are parsed by a harmony model, which selects the best chord sequence, and this chord sequence, which is the best chord sequence, is then added to the original input melody, which is then outputted as a MIDI file. So I will go through each of those individual steps. So in the generating part, we take a single track monophonic MIDI file, and we generate all those triadic chords for each of the melody notes that in the way that I just showed you. So for the first melody note, melody consists of a C, a B, a C, a D, E, and a C again. We're just going to create all the possible triadic chords for each of those melody notes. So for example, this C melody tone, this is the first one, this note, it's going to receive the chords C, A, and F, and this is because each of those chords contain the note C. And the same holds for the next melody tone. For the B, a B, a G, and an E is created. That's just because they all contain the note B. So what we end up with is a lot of ways to harmonize this melody, because each horizontal path here with diagonal steps is a possible harmonization for this melody. But there are a lot of boring harmonizations in these patterns, and a lot of chords that we know are just wrong in Western tonal music, which this is based on. So we need a kind of way to eliminate those illogical chords and those bad chords. And the way FHarm does this is by using 3 rules. We enforce cadences, which are specific sequences at the end of chord sequences that gives you a sense of resolution of the chord sequence. So they give you the feeling that the piece is done, which just gives you a nice ending. Then there's a rhythmical rule, and that says that we're going to remove chords that do not appear on strong metrical positions. So this is actually a parameter to FHarm, so you can choose how many metrical positions, strong metrical positions, you'd like to have chords. And the third step is, or the third rule is that FHarm removes illogical chord openings, or opening chords. These are just chords that we know in advance are just bad to open a sequence with. So what we end up with, for example, is this. We remove the A chord from the possibilities for the melody note C, because we know that this is just a bad chord to open a sequence with, for example. We remove all the chords from the second C note, because this note does not appear on a strong metrical position, because those are from this note, and this note, this note, and this note. So for the same holds for the last C note, all the chords are just deleted. So this, in a long melody, this greatly reduces the search space, but we still don't know why we should favor a C over an F for a melody note C, for example, or how to pick a chord here. We don't know what is better. For this, we are using something which is called the circle of fifths. This is a well-known geometrical representation of chords and notes that is widely used by composers and musicians. And the way we use it is that we look up the melody note, for example, a C, and we look up the lowest note of the chord, the possible chords that is in harmonization for that melody note, and the smaller the distance, the rim of the circle, the higher the probability is that that chord will be a harmonization of that note. So if we have a note C, and it can be harmonized with a C or an F, then C to C is, of course, the distance is 0, and to F, that's a much larger distance. So the probability of harmonizing it with the C is the largest. So then we end up with this. Every chord is given a probability, and we create a uniformly distributed random number. So we roll the dice, and we begin selecting chords to create the sequences. For example, what we could end up with is this. For the first C note, we select the C chord. For the B note, we select the G chord. For the D, the E, C. So this is a sequence of chords that is a valid harmonization of this melody. But if we roll the dice again, we end up with this sequence, for example, and we can do this a lot of times. So now we have another problem. We have a lot of sequence of chords, a lot of harmonizations for the same melody, but we need a way to find the best harmonization out of all these sequences. And what FHarm uses for this is harm trace. This is a harmony model that was written in Haskell, and in it contains style-specific models that we use to select the best sequence out of all those generated sequences. So we generate a lot of sequences. We feed it to the harm trace model that we choose. Currently, there's a pop model and a jazz model implemented, but you could implement any harmony model you like. And harm trace selects that model that is of that sequence of chords that is closest to the chosen model, and that is selected as the best sequence of the melody. So now we have the best melody out of all those, of the best harmonization out of all those generated sequences. The last thing we're going to do, or that FHarm does, is it takes that sequence and it smooths out the chord sequences. This means that the right inversions of chords need to be chosen for it to make sound nice, to make it sound smooth. If you don't do this, it's going to sound really mechanical, because every chord will be in root position. So the chord sequence is smoothed out, and then it's added to the original input file, and this is outputted to a MIDI file. So we started with a MIDI file, a single melody MIDI file, and we end up with a MIDI file that contains the input melody and the best sequence of chords that was selected by harm trace. So this shows that we can harmonize a melody, of course, but we found that we need to evaluate the results of FHarm, and we did this by creating 2 experiments. These were 2 qualitative experiments. In one experiment we used experts. Those were music and harmony experts that gave their professional opinion about the results by FHarm. And in the second experiment, we made a comparison between the output of FHarm with the textbook harmonization. So in the first experiment, we asked 3 experts to give their professional opinion on the harmonies that were created by FHarm. And these experts were a music professor, a musicology student, and a composer. The composer was a classical composer. And they were asked to give their opinion on a scale from 1 to 5, where 1 is best. The melodies were chosen out of harmony textbook by Walter Piston. So it's that way we could. There were exercises from that book, so we could see what the results were, and we could compare that as well. So they were asked to give their opinion on the technical and creative aspect of these generated sequences by FHarm. And this is one of the results, and this is representative of the results overall. I just want to pick out one. On the top you see the melody with the generated chords, and at the bottom you see the same chords with the scoring by the experts. So what you see immediately is that the third chord has a pretty bad score. This is mainly because of the smoothing algorithm. It shows it was too strict here. If you look at this chord, this is this G chord. It moves up here to this B flat chord, but as you can see, all notes are moving in the same direction. And this is considered bad practice in the classical harmony, or in the classical Western music. So this just sounds bad. So this is why, the reason why this chord was given a bad rating. So the conclusion of this is that for this chord, the smoothing algorithm was just too strict. We carried out, like I said, we used 3 harmonizations for this experiment. But if you want to see the results of that, you should look at the paper. They were detailed. The second experiment was a reharmonization of a melody by Walter Piston, so the same book where we took the input melodies for the previous